Okay, so with this, we are finishing the discussion about different types of defects in crystalline materials, right? So we talked about first point defects, and we learned that these are thermodynamically stable defects. What that means that at a finite temperature, there will be a certain number of point defects that are intrinsic and characteristic for that material. Then we talked about dislocations. We learned how they're introduced. So these are one-dimensional dislocations. We mentioned that they determine mechanical properties of the materials. And then we eventually learned about surfaces and other types of defects, surface defects, stacking faults, and we learned about the surface reconstruction. So just to complete this analysis, I would just simply like to mention that we learned about other types of materials that are not necessarily crystalline. And all of them have different types of defects. So one example would be defects in liquid crystalline materials. So we learned that liquid crystalline materials have orientational order, but they do not have positional order, right? So what that means is that there is some kind of an order. And every time when you break that particular order or any type of symmetry that you have in the material, this would be considered a defect. So what we learned is that, for example, in liquid crystalline materials, there is orientational order. What that means is that you have highly anisotropic molecules, and the orientation of these molecules that is common within the material is called a director in the liquid crystalline material. So it's simply a value that tells you what is the average orientation of all of the molecules. So if this was, a liquid crystalline material, there would not be a reason to have different colors in this optical image of a liquid crystalline material if this was a perfect liquid crystalline material. In other words, if this was the area of the material, and if all of the molecules were in the same direction, the image would look uniform, right? So there is no reason that the light would interact with the material in a different way here and here. And yet, very often in liquid crystalline materials, specifically when you make them in large scales, you observe these very beautiful, colorful images. What that indicates is that this director is preserved locally. So what that means is that here locally, where the image is blue, for example, the molecules might be in this orientation. Here, when the image is red, the molecules might be in a different orientation. What that means is that, again, on a local scale, the molecules of the liquid crystalline material are all in the orientational order. We can locally define the director itself, but globally, on a large scale, there is some kind of difference between these directors. And these types of defects, these interfaces, actually then tell you what is the border or what are the borders between different regions of the materials that have different directors. And these are called disclinations. So disclinations are defects in liquid crystalline materials, which are also considered to be one-dimensional defects. And just before we do go into specific about the disclinations, I would just like to mention that there are other types of defects that are more global in crystals. For example, if you have the material that either bends or splays, then what that means is that the director here might be slightly different than here, etc. But again, this is then typically defined by the borders or by the way how you process this material and what are the, for example, slides on the both sides, right? So you can deform this material in this particular case. But even when you look more globally within these types of liquid crystalline materials, you will see these types of disclinations that we just talked about. And again, in analogy to dislocations in crystalline materials, we can define certain types of descriptors that will tell us what is the type of disclination. And if you remember, when we talked about dislocations, we had a Berger circle. So in order to calculate what was the Berger's vector of a dislocation, we had to calculate and make the number of the steps and try to measure what would be the difference of that number of the steps in the perfect crystal and the crystal that contains a dislocation. So in similarity to dislocations, in the case of the liquid crystalline materials, we will do somehow similar analysis, but we will form so-called Frank-Nabarro circuits. So the Frank-Nabarro circuits will be simply the circuits which will tell us how the director is changing as you go along that circle itself. What that simply means is as follows. So if this is the orientation, so if these are two specific cases of the liquid crystalline materials, this will be the value which is called a strength of a disclination. So the strength of a disclination will be simply the descriptor, similarly to the case of Berger's vectoring dislocations, right? So it's called the strength of a disclination, and it is calculated or measured by Frank-Nabarro circuit. So what that simply means is that these are two different configurations and different ways how the local director fields are changing. And just to explain what that means is that, for example, in this particular case, the director in this position goes from left to right. And in this particular case, the director itself will be in this direction. So what that means is that we know that the director itself is a function of the position, and this director is changing in continuous fashion, right? So we see that it rotates, it goes from this direction and it rotates and eventually ends up here. In the second case, the situation is slightly different, right? The director goes here and then eventually it ends up here. So just to demonstrate what is the meaning of this strength of the disclination and how it's calculated using the Frank-Nabarro circuit, we will just look at this first example. And you can do this analysis for different types of defects or disclinations if you want at home, just to demonstrate the general principle and what this positive number means versus negative in the disclination strength, and also what is the meaning of this 1/2. So by doing very simple analysis, we will come to the conclusion that both the sign and the magnitude of the disclination have a certain meaning. Okay? So the analysis is relatively straightforward. So you basically start from a horizontal position, and you look at, and you then make a circle in the contraclockwise direction, and you measure the angle theta, which will be the angle between the horizontal position and as you make the circle itself. What you're then measuring is the direction of the director itself at a certain position. In other words, here, at the theta is equal to 0, the phi is equal to 0. For example, when you're at this position, so here the theta will be equal to pi, and the phi will be equal to pi halves. So we made a 180 degrees to go from the horizontal position to go to the negative side. And during that time, the phi angle, or the director, change from horizontal to vertical. So the strength of a disclination is then defined as 1/2 pi as an integral from 0 to 2 pi of the change of the d phi over d theta times d theta. So we are integrating over the circle itself, which is simply equal to the total change in the director itself over 2 pi. So if you look at this particular case, the sign here, plus, means that the theta and phi are rotating in the same direction. What that means is that as I'm making this circle, my angle is going in the contraclockwise direction. At the same time, the director is changing the direction in the same sign, right? So the meaning of the plus here means is that these two angles have the same trend or the same direction. The number 1/2 simply means that for theta equals 2 pi, the change in the phi is equal to pi. And therefore, the strength in this particular case is plus 1/2. In other words, when you make one full circle, the overall change in the director will be pi. Okay, so for that reason, it's plus and 1/2. And just to show you a couple of examples of the disclinations and different strengths, on the next slide, there are different configurations of disclinations with different magnitudes and size of the strengths, and you can see that they're very distinct in types of the configurations of the liquid crystalline molecules that they contain. Okay, and as a consequence, when you have a liquid crystalline material, these types of defects are very, very common. They can be caused, for example, if you're preparing, if you are dropping a liquid crystalline material into a glass slide, and there are small impurity particles in the glass. it's almost 100% sure that you will form these types of disclinations because the liquid crystalline materials will interact with that. There are other ways and other sometimes intentional ways to produce them, but as a consequence of these disclinations, I already showed you one example, but this would be yet another example of a very common texture of liquid crystalline materials, which is called Schlieren texture. Again, what you see in this particular image are these dots or these points within the liquid crystalline material around which the director or the change or the color of this image changes. So you see that they're somehow changing in continuous fashion. And by comparing these optical images, luckily liquid crystalline materials can be investigated very, very easily using optical microscopy. You can then recognize some of the features and different types of disclinations that we defined. Okay, so with this, we will stop for today, but we basically talked about surfaces, stacking faults, and we ended up with the understanding that different types of defects can exist in other materials that are not necessarily crystalline, and that there are ways to describe them. Because liquid crystalline materials are technologically very important, therefore understanding these defects and describing them is also important and very often used in literature.